informative one. A very warm good morning to everyone. I welcome you all to the fourth day of FDP funded by SER. I welcome our speaker of today's session, Dr. Sumit Shah sir from Intel. I request Dr. Sobibrata Shah sir, HOD of IT department, to come up and felicitate our guest, Dr. Sumit Shah sir, with a flower bouquet.
Welcome.
I would request our sir to come up and enlighten us on the topic standby power reduction technique using nano electromechanical switches.
Sir, it up to you.
Okay, so can I start now?
Yes, sir.
Yeah, so my topic is standby power reduction technique using names. For low power application, it is actually, as we know, that we are suppose in our phone, it is kind of 5 nanometer technology or 7 nanometer technology. So I will show that what is going on not only Intel, in across other technologies or other companies, what they are doing and what we are proposing using names instead of the traditional CMOS technology. So I am now currently working on Intel, and I did my PhD from IIT Bombay, and in a couple of months I visited to US. So I will show my PhD work and some PDF portal also. But it is confidential what I am working in Intel, so I will not present this to you. So in my talk, what I will show that overview of names, and you using that names, kind of now we are trending towards the names technology, not names, because when we are comparing with the scale CMOS technology, so we are names domain now. And then I will show some of the features like temperature reliability, issues in names, and some of the fabrication methodology, how you fabricate names itself. Okay, if you suppose fabrication facility is there, then how you fabricate names, like some kind of flavor, like 2-terminal, 3-terminal, and using that names, what is the application, real world application. And then I will conclude with talk. So now, if you see that scale of things, it means that in this, okay. The point. Point. So, suppose as we know, means why do you need to scale down, right? So scale of things means in this scale, if you see that we are now in 0.1 or 1 nanometer. So like means as a layman, so this thing it is made by 14 nanometer technology, 14. So now Intel is working on 7.5 nanometer technology. So that's why we need scale down. So if we see that first we have started with the mere computer, so vacuum tube 1 centimeter to nowadays 1 angstrom molecular based computer. Even it is same applicable in the biological molecules as well. So now, from that point of view, if we see that MEMS, micro electro mechanical switch system. Now, if we see that what is the fabrication kind of methodology of MEMS, same fabrication methodology. Suppose as we have the CMOS transistor, as we know in most PMOS, in the same silicon die, we can fabricate this kind of MEMS technology. And the benefit of MEMS is that as compared to CMOS technology, it's a very smaller in size. So why smaller in size? That packing density will be more. That is one aspect. The volume wise also it is less. Power consumption it is also less. So these are the benefits of MEMS. Okay. So based on that, if we see the what is the use of the MEMS. So in the traditional or some of present day life, as we see the sensor and actuators, that is the most common kind of use of MEMS. So like if we see the transducer, so transducer means from suppose one energy to other energy, that's the transformation. So like for the MEMS case, we know the sensors and the actuators. These are the two useful cases. The sensors, as we know that something in physical quantity like pressure, temperature, that will convert to the electrical signal. And actuator is kind of vice versa, means opposite actually, and that will convert to some action, like force, displacement. So this type of categorically if we divide, and sensor we have some, I just mentioned in that way. And in our application, like in your daily life, you use means the kind of MEMS-based sensors and actuators everywhere. So this is the input, means kind of input of sensor. I will show some of the pressure sensor and glucose monitoring, biological sensor, everything. It is kind of the principle is same. From some of the physical quantity it will take as an input, output it will give the electrical signal. And the actuator is opposite way, kind of accelerometer, gyroscope. This is the actuator example. So based on that, I just categorize some of the present days MEMS sensor. Like as we know, some pressure sensor. I have just some of the example, but it's not all. The big list is there. This is the very common biological sensor or biosensor. As we know that some of the means if you now go to the diagnostics center, so the glucose monitoring or any pressure-based sensor, cardiac sensor, everything it is based on MEMS cantilever-based sensor. How it works? That it is a 3-terminal cantilever. It is coated with some material which will attract it with the target molecule. So if the target molecule sits on that top electrode, that will bend actually, and that bend that will be converted to some resistance change. So in that way, cantilever-based biosensors works. And same thing, some of the MEMS-based sensors, that is health domain, as I told, even two sensors, sweat sensor, everything is happening around the world. So these are the sensor list. And this is the actuator, like most common actuation is the electrostatic actuation. Electrostatic actuation is basically, if you like, suppose two plates is there. So if you apply some voltage, this capacitance will change and this mechanical movement of this plate will happen. So that is electrostatic, and thermomechanical also. Suppose hot arm and cold arm. So based on their thermal means T or resistivity, that will bend down, and that bending that will convert to some electrical signal. So in that way, this thing works. Okay, actuators. Now, okay. So based on this overview, now I will come to the topic what I am going to show. So this is the MEMS overview, how it works and how it categorizes. So now I will focus on the electrostatic actuation only, because I will show why it is. So this is the electrostatic MEMS. Okay. So that is the main topic now. So in the electrostatic MEMS, what is a basic structure? Like two metal electrode. If you now apply some voltage, that is the off state. In between there is a gap. If you apply some voltage, based on the electrostatic force, it will come down and touches together. So based on that, it will give you the sharp constant current. Okay. And if it is suppose means it is not touched together, if you apply some low voltage, then it will be open. Okay. There is no current. So you will get the sharp characteristic, form of characteristic. So this is just I have mentioned the force balance equation. How it is so? Because we know the spring constant and spring theory in our class 10, 12 physics. Correct? So this force balance equation is basically electrostatic force and spring force. It will balance. But whenever someone suppose electrostatic force it is more than that, then it will come down and touch together. So this is the, as we know the CMOS technology. So in case of CMOS technology, we know the threshold voltage, right? When the current starts to flow from source to drain. The same way, in case of NEMS technology also, it is pulling voltage when the current means shoot up, okay, from offset to on-state. And the VPO is the pull-out voltage when it will come down from the offstate to on-state. Okay. So that is the one view of electronic MEMS. Now, if on a nutshell, if you see that why we use MEMS, why we use electrostatic MEMS, as compared to other MEMS. Okay. So this is the reason, merit of the electrostatic MEMS. I will show my next few slides why we use this MEMS. Because of ideally zero leakage, low parasitic capacitance, low add-on, infinite substitution slope. Substitution slope means there is means sharp characteristic, right? There is no gradual characteristic. That's why ideal infinite substitution slope is easy to fabricate device. Okay. Means, are you guys understanding what I am showing? Is it fine? We know CMOS technology, right? We all know CMOS, NMOS, PMOS, everything we know. So I will show now what I did, that instead of NMOS, PMOS, if you replace with this MEMS, how your performance will improve. So this is the merit of the electronic MEMS, and please keep this mind, keep this thing in your mind. I will show this thing only in my slides, other slides. Okay. So now that is the first slide of this topic, that why do you need some technology which will replace this existing CMOS technology? Correct. Because this phone, the main topic is that this phone still, suppose if it is in standby mode, okay, but still your battery keeps on deteriorating, right? It will not be fixed, correct? Why it is so? Everyone doing the research nowadays, even in industry also, it's an open challenge, open problem. So means now it is suppose 85% whatever. Whenever I will finish my talk, it will reduce, right? At least 2%, 3%. Why it is so? What is the problem underneath? Right? So
background action going on. Background action going on.
Even though if you off, correct, you can do that. Suppose you just uninstall everything. At the night, whenever you sleep, that time you just see the battery level. At least 1% also it will reduce. Why it is? And that is the open challenge. When I started the PhD in Bombay, okay, I got this challenge. I got this problem. Really, it's my problem. It was my problem. My guide was there. He told that yes, we have to invent some technology which can be replaced with the traditional CMOS technology. So that was the problem, okay. And you can come up also some solution, and that is the means Intel also industry problem. If you come up with some innovation, means any industry will take you. Okay. So that is the motivation. Okay. So why it is so? So because if you see this curve, the total energy dissipation, okay, E total, E dynamic, and E leakage. So E total means the E dynamic plus E leakage. Okay. So dynamic power dissipation, what it is called? When your means when it is the switching activity, when it is in active mode. Suppose you are means WhatsApp, everything is on. When you are talking with someone, That is the dynamic power dissipation. So it is series current F. That is the formula. Leakage is the something sometimes when it is in idle, non-active. That is this. So in case of traditional CMOS technology, still means everything is off, but still offset current that will always be, even though it is in picoampere. But in your chip, you are dealing with trillion of transistors, trillion. Nowadays, what we are making in Intel, the processor, it is very confidential. I will not tell you, but it is in below 5 nanometer. The number of transistors is 10 to the power 9. So if one transistor draws 1 picoampere of current, if you multiply it 10 to the power 9 into 1 picoampere, it will be huge. It is 1 milliamps kind of. So that's why nowadays what is happening, if you reduce the VDD, your leakage current keeps on increasing. Even though your dynamic power is decreasing, because VDD you are reducing, but your leakage that keeps on increasing, and because of that it's happening. If you uninstall everything, but because of this one, it will reduce your battery life. So that's why means every EDA company or every electronics company, they came up with some of the innovation. If you see that, like I think you all know, right? Parallel computing, pipeline, everything they means they introduced. But still, what I have told, if each core kind of, we know, right? Multi-core, dual core, it is finished. Multi-core nowadays. Intel now introduced i7, I think, i9 also came. So if each core operating, suppose 1 picoampere, then if you multiply with that number of cores, it will draw 1 milliampere of current, and that will huge as compared to the dynamic power. So that's why that is the dominating factor, how to reduce that. That's why we need some technology which will give you the low leakage, meaning offset current, and give you the infinite separator state. Means whenever it is in off state, that time it should not draw any current. Correct? That is the motivation. That's why that is the motivation. So we need some technology. That's why I need names, because as I have shown you, right? This technology, it will give you the ideally zero leakage. Why? When it is in off state, there is no current. Right? Okay. So nano electromechanical switch. So that is the first one. What I have done. Okay. So first, when I started, that time I don't know what is the names. So that is the research criteria, right? So first, when you started some topic, so first you get that whatever is happening around the world, right? So I took some of the paper, what is already done by someone. Okay? So I took some of the 40 names, and this is the cantilever name structure. So I modeled just. I just modeled it for the very circuit simulation. I modeled, it's like a RC based structure. Okay. I means RC based structure, and then I just calibrated, because suppose we are doing all research kind of, right? It means we have to publish some paper, correct? So for publication perspective, always we have to keep in your mind that we need some calibration, correct? We need calibration. Calibration why? You can claim anything. I have done this, that. But no, means that will not publish in a reputed journal. You have to compare your result with experimental result. Then only it will be published some reputed journal, right? So that's why we need calibration with the verification or the verified with some experimental values. So we did that, and then so that was the first approach. And this is 14 nanometer FinFET model, and the same thing. This phone actually is made by this device. Okay, it is Samsung 12 Pro. So it is made by this device, 14 nanometer FinFET. But now, if you suppose buy iPhone, correct? So iPhone is not made by 14. It is less than that. I will not tell you what is the technology node, but it is below 10. Okay. So if you saw some of the FinFET device model, so this is the FinFET model. I will not go into the detail. So FinFET is why it is replaced with the planar MOSFET. Why it is so? Because we need good gate control. I think all of we know, right? What is the MOSFET transistor, right? Kind of gate drain source, right? So why we transition towards the FinFET model and now nanowire gate? Why it is so? What is the reason? Can you please say something? Why we have transitioned from the planar MOSFET to now 3D? Like, what is the problem? Is why it is so? Anybody else? So means we all know kind of 2D transistor, right? We got correct, means gate, source, drain. Correct, no? That we know, right? So if we think of kind of this is the source, gate, drain. So in case of 2D, whenever the current starts to flow, when the channel is on, right? When the channel is off, that time also some current will flow. So to prevent that thing, we introduce this FinFET model, and that is also Intel patented technology. Intel only first time invented, right? This FinFET model. So this is the gate. This means this Z direction, this way. So this gate is controlled over fully controlled, right? In the 3 direction. This way, this way, this way. So the leakage component is less, very less, as compared to the 2D transistor. That's why FinFET means gate. So I did that, and then this thing is done in some TCAD model, TCAD software, and then this is the calibration with the experimental device. So the bottom line is that I introduce names. Means I suppose simulated. I think we know all the circuit simulation, right? We did some circuit simulation in our life, right? So in circuit simulation software like Cadence and some Spice simulator. So if you, this is the inverter chain, okay? Inverter circuit, all we know, right? Correct? Inverter circuit we know, right? Or not? We don't know. Inverter circuit we know, right? So in case of this 17-stage inverter chain, if you design in any software, circuit software, and to reduce the leakage, there are some mechanism. So the common technique is that the power getting technique. So if this power getting switch, if it is off, then this path is off actually from the VCC to your circuit, it is off. So you think of that time there is no leakage current. Whenever this path is on, that time this circuit works. So that is the technique, power getting technique. So this and this technique is the real world technique. Even everywhere, means this phone, in laptop, everywhere. Okay, this technique used in circuits to minimize the leakage power and kind of. So I put names in this place. That is the most critical part. So that's why instead of FinFET, I use names. So that is the card. If you see, after suppose 10 to the power 4 nanosecond, some millisecond coming up, if you convert it, so that time onwards names is beneficial as compared to the FinFET. So that is the bottom line. If your standby mode means if your phone, if it is long standby mode operation, if you use the names technology, then it will be beneficial. Kind of, it will give you. It means if you use names, your battery deterioration means not zero, but much lesser than the traditional one. Now what it is. So that is the first paper what we have published, okay, in IEEE real, and that was recognized in their cover letter because first time we have published this thing. So after that, what we did as temperature reliability issues. So some of the whenever first you introduce some of the new technology, you have to do lot of things. Okay. So in your research, suppose if you invent something, you have to prove many things. So that's why I suppose propose these names. So I have to show many aspects. So that's why the temperature reliability came, because reviewer they asked many questions. So what is the reliability of this? Based on that, this thing works. So this is the same thing. Same means this time still I am in simulation phase, and in this simulation also I use the someone's fabricated device, and then I modeled and it is calibrated. So I will just show that what is the approach and what I have followed. Okay. So this thing has been simulated in some Coventerware. In Coventerware console, I think you heard, right? Console Coventerware. Okay. Whatever. So this MEMS-based simulation software. So in that software, you can design your MEMS technology, whatever the MEMS device, and I calibrated, and then this is the I have introduced one more thing. That is the nano FET. Nano FET, what it is? So it is gate all around. Okay, there is no leakage almost, because it is controlled with overall means fully actually. So we expect zero leakage. So based on that, I will just show that is a calibration characteristic. The same stage means buffer chain I have used, and I will and the same power getting technique. I just means changed with the FinFET, nano FET, and names. Okay, and I will show what is the improvement. Okay, so this is the simple. Yeah. That is the main card. If you see this thing, the same actually means if you go to some suppose Kashmir, okay, now the temperature is very low, correct? And now if you go to opposite side, Andaman side, temperature is very high. The same thing in the chip itself. If you increase your temperature, okay, and even heating is the main reliability concern nowadays. So if the temperature increases, your leakage power increases exponentially. Okay. So the green one is the MEMS, blue is the nano FET, and red is the FinFET. So it is made by FinFET. Okay. So the real problem is that suppose you are talking with your friend for a long time. So that will get heated up. If it is heating, so your leakage power that will increase exponentially. So your battery deterioration that will do much faster. So that is the main problem. It is a very challenging problem. Okay, that's why I am showing. So if you introduce names, you can tackle these challenges. So that is the motivation of doing this thing, and that was also published in IEEE. So yeah, so that is the same thing. Energy gain is what I am showing that some point of time. Suppose you are talking with your friend for 5 to 10 minutes. That time there is no difference with the existing CMOS one, whatever you have in your phone with the nails. But when you will see the main difference, whenever suppose if you are talking with 2 hours, 3 hours with your friends, okay. So that time it will get heated up, it will draw a lot of leakage energy, and your battery keeps on deterioration much faster. So then that time if you use nails, so that will give you means the deterioration rate will be very less. Okay. So that is the motivation. If you see the energy gain the card also. Okay. So that is a simulation what I have done. Okay. Now after suppose in your PhD it is almost 4 to 5 years, right? Journey. So after this simulation work, what we thought that we have to go the real device application, right? We need some device, because till that point what I did, I took someone's paper, I modeled it, I calibrated with experimental result that I also took from someone's, and then I did some simulation, I show the result. But that is not a PhD work. Okay. In your PhD you have to invent something. Okay. And world means you will be recognized by your invention. Okay, in your PhD. So that's why we went with the fabrication. So fabrication that will means unknown problem. If you go to the fabrication, it is very challenging. Okay. So first, always you have to do some simulation because you have to make the specification. Okay. So that is a simulation what we have done for two terminal names. As I saw that two metal plate, right? It is a simple structure. The world's simple structure, I can say. Just two top and bottom metal electrode, and it is anchor. Okay. So it is separated by an air gap. It is a very low air gap. It is 20 to 30 nanometer. It is separated by an air gap. Whenever you are applying some voltage, so that will touches together. Okay. Means that touches together, and then you will get some current. What I show you earlier, right? So if you see that air gap is 25 nanometer. So 25 nanometer we cannot see in your eye also. Okay. It is very less. So yeah, means that is the fabrication flow. I will not go into the detail, but that is the flow what I have done and what I have shown, that in that way you can fabricate your names device. Okay. Yeah. After suppose 6 to 7 months trial, and so we came up with this device, and this is the actual fabrication image. Okay. So this is the gap. If you apply the voltage, it will come down and touches together, and then we will get the line. So that is a real device fabrication what we did in Bombay. So yeah, some of the characterization, AFM image. Yeah. So that is the final thing. What is the electrical characterization? Okay. So if you see the leakage current is very less, it is in picoampere. It is almost zero kind of, and you will get a sharp characteristic. Are you with that? Means, are you understanding what I am showing out? Just boring kind of. Is it so? What it is? Please tell me. Just to clarify, even though you are feeling bored, okay. But I mean, what I can say that from industry point of view, this is the open challenge problem. Okay. What I did in my PhD, it's an open challenge. So not only from Intel, if you go to, we are all from electronics background, right?
No.
IT. Okay, fine. Means IT and electronics nowadays it is kind of together, right? But it's a common problem. Why it is so? Because what I am doing in Intel now, it's same thing what you do in case of IT. Because everything we are doing in Python, Java, everything. Okay, so I am not in now electronics nowadays. So only software background I am working on. But apart from that, but my background is in electronics, right? I did my PhD in electronics. So what I am saying that is the common problem. Even though your background is IT, computer science, whatever, but still you are using phone or battery, or laptop, anything, any low power electronic gadget. This problem persists. This problem is everywhere. Your battery keeps on deteriorating if it is in standby mode. So how to prevent that problem? Okay. Means I think in your IT also you can think of. Means we have to come up with some technology. Means whatever the existing technology, that will not be the solution. Okay, we have to come up with some technology that will prevent or that will tackle this problem, so that your battery deterioration rate that will be much less as compared to now. That is the underlying problem. Okay, so then I will not go into detail maybe because this is core problem. But fine, okay. Then I will kind of different flavor of names why we used, because 2 terminal, 3 terminal, because as we know the transistor, it is source drain gate, right? 3 terminal device. So 3 terminal means we need some control terminal. Means control means the gate terminal. Means suppose if you open your tap, okay, then only the water will flow, right? So that tap means the controlling that tap is basically the gate terminal. If you apply some gate voltage beyond threshold, then only this source and drain will touch. Okay. Otherwise, will not. So this is the on state and off state. So okay, so that is the fabrication flow. I will just show the different fabricated device what we have done. So this is the till now. I mean, all over world actually. This is the lowest cooling voltage nails technology. This device, okay, it is 50 millivolt. We need only 50 millivolt to turn on this device. So this thing is patented also. So this is a device calculation. I will not go this thing. But yeah, so the thing is that I think the problem is clear, right? The problem is clear. So after problem, so this is the solution is that why we are trying to replace with this device, because if you see the characteristic, you are getting the 1 milliampere of current. It is high enough. That is the on state, and your low state it is almost zero. If you see this picoampere, the 10 to the power minus 12, it almost tends to be 0 ampere. So that's why we are thinking that we can replace this phone or the existing technology with MEMS. Because in the off state it is giving 0 current. So even though it is in standby mode, I will end up with 0 leakage or 0 battery deterioration. But whenever it is in on, then it will be act as a same as the CMOS technology. So okay, that is the I will not show this thing. And this is the basically what is the reliability means, because this phone is switch on switch off every time we do, right? So what is the reliability? If means how many cycles it will work. So this type of test we have done. Okay, whatever. So now I will show some application. So DC-DC boost converter in energy harvesting circuit using MEMS. We know some energy harvesting circuit. I think we don't know, right? Have you heard this technology? This terminology, DC-DC boost converter. Any of you know that thing? We don't know, right? So what it is? Okay. Suppose you are IT CSE background, but anyway you have to know that what it is actually. Just talking and that's it. It's not, right. We are educated person, correct? So what is the need of this DC-DC boost converter? So in this phone there are multiple circuits, right? Many modules. Even this laptop also many modules. So in each module they need some different voltage, not one voltage. Suppose in this from the pole it is 330 volt AC main, right? And when it is coming in this room's board, it will be something 5 volt kind of, right? So how this 330 to 5 volt is coming? There is some circuit, right? And in this phone it needs 0.7 volt. So whenever you are when your circuit, suppose panel, there is some board, no? So in this board the voltage is coming 5 volt, but this laptop or this phone it needs 0.7 volt. So who will do that job, right? Hello, excuse me. Okay, I think you are busy. Just one question, huh? Just one question. The question is that in this circuit, this panel, electrical panel or electric board, from the AC main, suppose it is coming 12 volt or 5 volt, but your laptop, your battery, it needs whatever the internal circuits are there, it needs only 0.7 volt or 1 volt. We need some conversion, right? From 5 volt to 1 volt. Otherwise it will burn out, right? Who will do that?
The currents are direct.
Adapted to this one. This whatever we are connected to the laptop, right? So who will do that? There is some circuit circuit inside, who will convert? So that is the means this is convert. So there is two terminology in circuit era, either boost or buck. Sometimes you need 5 volt to 0.7 reduction, sometimes opposite, 0.7 to 5 volt. So this is the very common circuit. Okay, clear. So in this circuit, if you use names, I will show that what is the beneficial you will get. So okay, I will not go into the detail of circuit, but yeah, that is the means names Verilog model we did, and that is the actual circuit in this phone. Okay, boost converter circuit. This is the, it looks like this. Okay, so we designed this circuit, and the critical transistor is that this one. Okay, and I replace this transistor with the names what we have fabricated. So I will show just quickly the results. That will be the good one. Yeah. So if you see that is the ultimate thing. So we all know the boost converter right nowadays. Now after this discussion. So yeah. So the efficiency. If you see the NMOS, NMOS is this one, and these are names. This 66%. And it will give you the 40%. Okay, so 30% efficiency improvement at particular switching frequency. So what is the switching frequency? What is the switching frequency? Right? We don't know switching frequency, right? We don't know switching. So the switching frequency is that, suppose if you want to send one message in WhatsApp to her, how fast it will go? That is the clock frequency. Network speed, that is fine, but you are sending from your device, that should catch the means whatever the Vodafone, whatever. But your frequency should be fast enough to catch that network. So nowadays the existing phone, it will operate at gigahertz speed. Okay, nowadays they are implementing coming now. iPhone is a terahertz. So okay, so now this is in the gigahertz range. So it is too fast, right? So it's for the means to show that way. I use the kilohertz, but still you can go towards the gigahertz range. But that is the bottom line, that if you use names in the harvester circuit in your phone, whatever existing, if you use names, you will get the efficiency improvement. Okay, so I have shown some experimental demonstration. I did actual experiment. Okay, what it is in the phone, in manual phone. I designed that, and I show that is the efficiency improvement we will get. Okay, so I'll just show the application what I have done, and that is recognized. Okay, and we have published many papers in IEEE. So here is the one of the application, very interesting application, because we all know AI, ML, right? Everywhere. Even child also know, right? So that is the neuron circuit. I will not go into details, but the neuron, what it is, okay? So neuromorphic computing, your neuron that is mimicked with this circuit, means not circuit I will show, but your neuron basically it will be formed as a spike, okay? Because in your brain something always we can mimic as a current spike, okay? So that is the leakage and integrated fire circuit, but I will just quickly this thing I will show. So this is the neuron equivalent electrical circuit, what we proposed. Okay. So that thing also, it is in conference, but it is I went abroad actually to present this thing, because we first introduced this thing, but always I inspired from this paper. But that is the first time we have introduced this neuron, whatever we have right in our brain. Neurons, synapse, dendrite, axon, we all read in biology, correct? Huh? So that equivalent circuit this thing. So I will not show this thing, but I will show the result. So yeah, I just explained how it is so, but I can just as a overall the brain neuromorphic computing, you all know, right, this terminology, that neuron is modeled with this circuit. So yeah, with this circuit I introduced names some of the critical path. So that is the form of spikes actually. Okay. So suppose if you remember something, so I have told you today. Suppose if you want to recall after 5 days, so it will be in the form of spikes. So that in that way I modeled kind of this circuit, and this is the model of spikes. Okay. So just yeah, that is the result is basically, if you see the energy per spike, this is the black one with the CMOS, and this is the big names. Okay. It is much reduction. We have claimed that some 8% of improvement if you use names. So yeah, means we just touched upon all the application, all the possible application with names. And the last one is the 40 names. The 40 names, actually we use these names in the actual CMOS digital circuits. We all know actually in IT, CSE we read, right? Analog circuit, digital and or gate, whatever. So in that digital circuit, if you use names, what is the efficiency improvement you will get out of it? So I will not go in this thing 40 names, this thing. That is the actual device fabrication, what we have done. This is a device characterization. I will show the actual electrical characterization. Yeah, that is the good characteristic I got. Okay, everything is fine, and now I will. Yeah, that is the state of art. We publish this thing. It's okay. Yeah, that is the benchmark circuit. What we have designed. So if you see the C17 this thing, it is ALU and control circuit. I think we all know, right? CSE guys, the priority encoder and NAND gate module. So why it is so? Because we used these digital circuits as a ISCAS 85 benchmark. Why it is so? Because I also designed or simulated with the processor also. Because we want to see that with the processor how these names will behave. If you introduce names as a power getting switch or power getting block, and your underlying circuit is processor, then what is the efficiency you will get out of it? So it is the same actually what I have fabricated, I modeled it. Yeah, so that is the actual thing, energy gain in case of these digital circuits. After 10 to the minus 2. So what is T on by T off? What is T on by T off? In this energy gain, what is the curve actually? Someone will tell me that what is the, even though you are, suppose IT, CSE, it doesn't matter, right? It is science, correct? So what is this energy gain by T on by T off? What is it? And suppose if I want to ask, if you tell me this terminology in respect of this phone, what is it? So T on by T of what it is? T on by T of means yeah, times obviously. So means whatever time it is off and whenever it is on. So on time and off time. Now it is off, correct? Whenever it is active mode, it means whenever I am talking with someone, that is active. So that is the active time by idle time. That is the T on by T. That is the terminology. Energy gain, what it is? Don't know. That is the formula. Formula means whatever. Okay. The formula is basically active power plus switching power plus whenever the off means the off state power. So the total power dissipation, what it is? Whenever it is active mode, that time whatever the power it is drawing, whenever it is off state, whatever the power it is drawing, and whenever it is switching off to on. So that is the 3 power every circuit goes. Okay, please keep this in your mind, because it means anywhere you may ask, means someone can ask you that what is the power of this, what is the power dissipation formula. Nobody will ask you the actual formula because we will forget. But that is the means terminology. If you understand it, whenever it is in on state, whatever the power dissipation, whenever it is in switching mode on to off, that power dissipation some power. Whenever it is in off state, that time also some power dissipation is there. So if you sum it up, so whatever the power you will get, that is the ECMOS. And the same thing whenever you use the names, whatever the power, so that is, if you divide it, that is the energy. So it means whenever it crosses 1, so that is the 1, right? And because 0 means 1. So if it is 1, so it means it is greater than 1. So ECMOS greater than E names. So E names is come, na? It is less, right? So that's why from that point onwards, name is beneficial as compared to your traditional name. So this is the ultimate means that I have almost finished. Okay. So here is the final application what I have shown. So we have covered all application, all possible application, realistic application. So now the last thing is that we need some scaling rule. I told, right? So it is in 14 nanometer technology. This thing 14. Now Intel is working on 5 nanometer. Even below that, but I will not tell you what is it. But it means it is made by transistor, correct? It is made by FinFET, what I have shown you, FinFET technology. So in case of transistor, there is a roadmap. What is the scaling phenomenon? Means there is a roadmap, correct? From 14 to 5, then till 1, what beyond I don't know. We don't know what is beyond that. But still scaling phenomena that will work. Okay. That is called Gordon's Moore's law. Moore's law. You know, right? I think we know, correct? Moore's law. That is whenever someone, you, your children or whatever, even after 50 years also, someone will get into the electronics domain or VLSI domain or chip design domain. That law will exist after 50 years also. Always keep in your mind that Moore's law means I fortunate that he is the Intel founder. I am working from home, but I went to Bangalore also. But in video conference I saw him. Okay. So the Moore's law, what he invented, what he told to the world, that after every 18 months, number of transistors that will get doubled. After 18 months. Still Intel is following, not only Intel, every company is following, trying to follow. So that's why they invent many devices like FinFET, NanoFET, some many other things are also coming up. So that's why we have in transistor, what is the law? Moore's law is correct. So in that way, in names also, I just means I presented some law. It's not invention, but I proposed some law that was published somewhere. Okay, so that is the scaling approach. From so suppose if you are now coming towards this, if you wish to work with this, you can follow this scaling phenomena, scaling approach. So some scaling rule I proposed, and I validated with the experimental result, whatever I have already presented, the fabrication result, and my model is almost validated. So yeah, we publish this thing, and yeah, that is the conclusion. I will not go into the every bullet point, but yeah, on the underlying statement, we know the problem, right? We all know the problem, correct? So how to tackle this offset leakage current, correct? So to prevent this leakage issue, I personally came up in my PhD this names technology. If you replace these names with CMOS, existing CMOS, to some extent you can prevent this leakage issue. Leakage in a layman way, if you ask your battery deterioration, right? If it is in standby mode, still your battery keeps on deteriorating. So that is the, whenever you go to home, remember that thing. That is the open problem, and names is one of the promising technology. It can be replaced with this. Okay, that is the publication.
What a wonderful session it was. It was very new for us, but it made me more curious to know about these all things and how the transistors, CMOS, and everything. It boosts our last year stage and also. So, I would like to request Judy ma'am to come here and give a presentation. Ma'am, please. It's a small gift from us.
Yes.
So after this session, there is a tea break, and after tea break, we will meet in lab 4 because the next session we are having online. So after the tea break, 20 minutes to 50 minutes, we will meet in lab 4. First.